Okay, we're doing a warm-up problem right now. It has to do with percent composition. Find the percent composition of each element in Rust. And tell yourself, I should be able to do this, right? Even if they ask me next year. What if they ask me next year in college? I can do this problem. What's the key to percent? What's always the key to percent? You always divide by what? The total. Now, are you going to do this problem in the AMU world? Or are you going to do it in the mole-gram world? All right? Whatever you feel comfortable with, you get the same answer. Does anybody need a calculator? Okay. I know it's not for a grade, but act like I'm going to get this right. My goal is to get this right. And if I miss it, I'm going to learn something from it. So rust is called iron 3 oxide. Iron 3 oxide. Problem like this might even come. NASA has started to make a new push to go to the moon and actually have people stay there. Even though I was disappointed that NASA kind of abandoned their shuttle program without having in replace of it, they're pushing toward moon colonization. And then they want to use the moon as a place to take off from to go to Mars. Chances are, by the time we get there, China would have probably already gone to Mars and skipped the moon. Now, they may have killed a few people on the way, but they may do, some countries may just do that. Let's skip that step. Let's just go to Mars and, made that mistake. They what?
I think they already sent stuff to Mars.
Oh, we've sent probes to Mars.
I think they did it.
Do you think they sent people? I'd never heard that.
They sent like a rover, a drone, and some other stuff, but they did it all at the same time.
There's no one
Instead of
doing
it
it
separately.
And
We did it separately, I think.
you're talking about the moon?
And Mars.
Oh, Mars. It's interesting because there's some politics involved. There's finances. You know, are you willing to give the money to NASA or not? Is it worth something? I know when we had the moon program, it was a huge amount of national pride. And it was huge. Like the whole country was kind of like together. As a matter of fact, I'd watch people around the world, everywhere in the world, they were watching TVs. And it was like great. It was almost like the human race decided that they were together instead of fighting each other. So I don't know how much that's worth, but it seems like that's worth a lot to me. I wish we could do that. All right, so everybody finished? I just made this problem up, and so what we need to do is we need to know what the total mass is. I'm going to probably stay in the gram mole world. So iron is 55.8, and there are two of them. So it's 55.8 times 2. And then we have 3 oxygens. 3 times 16 is 48. Now, if somebody add those up for me, Sydney, did you have this already? I think it's going to end in a 6.
Yes. 159.6.
Okay. Now, what we really want to know is we don't have to do everything. It just asks for the percent of everything, each element. So 159.6 is the total, but how much was contributed by iron? Iron was 6, 1. Is that right? Is that what you had? Is that 111.6? Okay, so Sydney, what do you have for this one?
69.9%.
How much?
69.9% of iron.
Okay, and it probably came out to be 0.699, and you changed that to percent, didn't you? Okay, and then the rest of them, I could actually do it the other way. I could do 48 over 159.6, or what's another way of finding this one? What's another way of doing this one? Yeah, couldn't I take 100% minus this? Isn't that right? Is that what you said, Kyle? What'd you get?
30.1%.
30.1 or something like that?
Yeah.
Okay. Everybody okay on that? Most people do pretty well on percent composition, and then you throw in this curveball here, and then some people, they don't know what to do with it. What if I said that we found $50,000 and you get 69.9% of it if you can tell me how much I'm supposed to give you? Could you figure that one out? So what's the difference between 50 kilograms money-wise, $50, for example? And so how do you do this? You say, well, there's 50 kilograms, and every bit of that is how much iron? 0.699, isn't that right? Is that right or not? No matter how much of this stuff I give you, this rust stuff, that percent of it is iron. And did anybody, what'd you get for this one? How many kilograms?
34.95.
And I'm going to see if that's reasonable, because it's got to be over half, about 70%, right? 70% would be about 35. You're right on the nose. I think you did it right. What do you think about that? Now, when I do go to the moon, you know what they'd like to do is they'd like to make things like maybe out of aluminum. And so what do you mean? Aluminum? Where's no aluminum on the Mars? Yeah, on the moon? Yeah. But it's in a rock form, isn't it? It might be aluminum chloride or aluminum oxide, whatever's in there on the moon. And they might do the same thing. We have 3 tons of this rock. How much aluminum can we get out of that? And so they might be calculating that stuff right now. Yes.
Is aluminum hard to purify?
Is what?
Is aluminum hard to purify?
Well, when it comes on the Earth, it's kind of an orangish dirt, and it's called bauxite. You would never think that you'd get a shiny silvery metal out of this clay-like looking stuff. So I don't know. At one time, on the top of the you've probably read that in the book. On the top of the Washington Monument, they wanted to make this so special. They wanted to put something really, really valuable at the top. And guess what they put on there? Aluminum. At that time, it was way more expensive, hard to get that than gold. It was more expensive than gold. And now, even today, some of you throw your aluminum cans away, don't you? So somebody learned how to get aluminum out of the dirt, a new method that was a lot cheaper. So those are great questions you're asking. Okay, next, we found out that if you're doing percent composition, why would you do that? Why do we even need to know it? Well, one way is I might want to do this. I might want to find that out. Here's another one. What if I tell you the percent composition? Here, you had to figure out the percent composition, didn't you? What if I tell you the percent composition? Well, this is what we did yesterday. What if I say it's 89% oxygen and 11% hydrogen? I'll let you tell you that. And then I'll say, but I don't know what the formula is. How did we do that yesterday? How did we go from the percent composition to the formula? Whoops, I didn't find it. How do we go to percent composition to formula? How was it?
Well, we first said that are we saying it's 80% in terms of mass?
Yes. Now,
Okay.
unless I tell you differently, when they do percent composition, it's by mass.
Yeah.
Later, we'll talk about percent composition by volume, but right now, I'd say mass. Good question.
So we first, we assumed that they're doing us 100
Right.
grams of
And why do you do that?
Because it's easy to convert in terms of
Right.
percentages.
How much of this stuff did you give me? I'm not telling you. Okay, I'll pick my own number. And I'm not dumb. I'm going to pick a 100-gram sample. Why would you do that? Because if 89% of it is oxygen and it's 100 grams, then what's that mean? 89 grams was oxygen, right? And then this would be 11 grams was hydrogen. Now, maybe this, I don't want this to go over your head, but yesterday I was asking about what world are you in when you look at any kind of formula, whether it's an empirical formula, a molecular formula. If you're in any kind of formula, what world is that? And it's not the mass world, I can guarantee you. This is not 6 grams of that. See, it's not the mass world. What is it? The mole world, it's a number of particle world, isn't it? So if you have a problem and they give you percent compositions, you're into grams, but you're not done yet, are you? What world do you have to get into? Moles. And that's what we did yesterday. Look, we changed that to grams, and they said, but I got it in the mole world. And what's his shortcut? What's his shortcut? If you're in gram world, if you're going to go down the mole world, what do you do? Divide by the molar mass. Okay? And that's what we did yesterday, isn't it? And so that got us into the mole world, and then we had these weird-looking numbers. Look at that. There's some weird-looking numbers there. And scientists get this all the time. But scientists know a little math trick. What's that little math trick that can tame these numbers and get them closer to a whole number ratio? Right. So see this number here? And you know what? 1.73, 1.74, it's not going to make a difference which one you pick. But that's all right. Let's pick the smallest, right? And so you divide this by, oh wait, by the way, this was the smallest one. I made that mistake yesterday, didn't I? So you divide everybody by the smallest. This is going to come out 1. This is 4, 6, 4. And what I do know is that for every 4 carbons, remember what happens in the mole world is what's happening in the little world, isn't it? For every 4 moles of carbon, there's 1 mole of cadmium, 6 moles of hydrogen, or in the little world, 1 atom, 4 atoms like that. Now the next little trick we did was, okay, that's called the empirical formula. It's the lowest whole number ratio, right? But now you could do another experiment to figure out the molar mass. They have some pretty neat homework questions if you take the time to do them. For example, they might do it like this. You do a problem and you go, blah, 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 and you find out how many moles you have, okay? And then you go something else, and then you find out how many grams are in, okay? And you got, hey, I got grams and I got moles. Well, what is grams per mole? What is grams per mole? What is it? It is. That's molar mass. So if you do an experiment and you know how many grams of something there are, and you do a little stoichiometry and find out how many moles there were, guess what? I figured out the molar mass. Got it? So now, when you go back here, I have the empirical formula, and here's what we do. Neat little trick. What is the mass of the empirical formula? I'll sometimes call the empirical mass. And this came out to be 230. But what if I do another experiment, and it shows me that molar mass is 230? What does that mean? The empirical formula weighs 230, and the actual compound weighs 230. That must be the chemical. That must be the chemical formula. But what if I do an experiment and I find out the molar mass is 460? The empirical is 230, but the molar mass is 460. You say, well, that'll go in there twice, won't it? So what do? You double all those numbers. Okay, so what I'm trying to show you is, even though when I was sort of taught how to do these, I just thought I had to memorize at least 11 or 12 different kinds of problems. Are you seeing at least some kind of commonality here? Now, here's another one. I didn't do one of these, but I'll show you how it works. Watch this right here. Let's see how fast you can give me the empirical formula. And we're going for speed a little bit here, right? Oh, wait, what do you mean empirical formula? You're giving me grams. You're giving me grams. Yeah, that's right. What are you going to do if I give you grams? You're going to stay in the gram world? Then get out of it. What are you going to do? Okay, do it. What are you going to do here? Divided by the molar mass of carbon. So what's that going to be? What's 24 divided by 12? 2. And this guy?
Let's say 6 or 16.
And this guy? 16 divided by 16. Okay. Now again, 6.05 is 6. You get that? Okay. So what's my final answer? My empirical formula is going to be C. For every 2 C's, there are what? 6 H's and 1 O. Okay, now let's add this up. What is the mass of this empirical formula? Now you know empirical formulas are always reduced, right? Aren't they? They're always reduced. All right, so what's the mass of this guy? Oh, I can't do this, can I? 24, 30, 46. So the empirical formula has a mass of 46. So what if you find out that the molar mass is 138? Well, the empirical formula weighs how much? How many times will that go into this? How many of these empirical units will I need? One of them? No, that's not enough. Two? That would be 92. That's not enough. Three? Does that work? So if I find out I need 3 empirical units, then I multiply all of this by 3. And what's my final answer? C6, 18, 06. Now again, they have great problems in the book, and they even show you the solution, and I'm just trying to make you feel comfortable when you see these kind of problems. Are you okay with percent composition, going to empirical? Go to molecular. How about grams to moles to empirical formula? This one, by the way, I just thought about something. Sorry, I thought about something. Luckily, one of these numbers was 1. Because aren't I supposed to divide by the smallest? Okay, so I almost skipped a step there, but if I do divide by 1, I get the same numbers, don't I? Okay, now, I want to show you one more thing, and then we'll do something different. What if you get something like this? What if you get a ratio of 2, 2.5, 3? That cannot be your final answer. That's not the lowest whole number ratio. So what are you going to do if one of your numbers is like 2.5, 3.5, 1.5? What are you going to multiply your thing by? 2. You become 4, you become 5, and you become 6. Let's try another one. Let's say we get 2.33 and 2. 2.33 is not 2. How do you get rid of a third? How do you make a third into a whole number? We knew that a half to make a whole number multiplied by 2, so you're going to multiply by 3. Won't that give you a whole number? So multiply everything times 3, and your final answer will be, what's 3 times 2 1/3? 7. Got that? How about this one? What are you going to do if the ratio comes out to be, and by the way, 1.67 is what? 2/3. Oh, that's that third thing again. Huh? What are you going to multiply? What's the denominator for 2/3? 3. Let's multiply by 3. And that'll be 9 here. And what's 1 2/3 times 3? What is it?
5.
That's it? Everybody got that? Okay. Well, now what I thought we'd do is they have a really, I think, a really good problem on page 91. Now, if you don't have your book with you, that's fine, but I'm going to go to page 91. And my plan is to do this problem and then do a stoichiometry problem. And that should be enough. 91, did I say 91? Yeah, here it is. I'm going to tell you, I first started using this book, this author, Zumgo, his name, probably about 16 years ago. And I was, I'm going to teach out of this book, and so I guess I need to know how to do the problems. And when I first read this, it was a little bit confusing because I hadn't seen a problem like this. You normally don't see a problem like this in first year chemistry, even honors. But let's take a look right here. It says here, what they're going to do is suppose, here it goes right here, suppose that a substance has been prepared that we do know is made of carbon, hydrogen, and nitrogen. When a 0.1156 grams of this compound reacts with oxygen, it forms this much carbon dioxide and this much water. He said, what? I think you lost me on that. So let's see if we can draw a picture of that, okay? Now, if you don't have that book with you, I have the numbers here, but let's try that again. Here's what I know. I know that this sample that they gave me, I know you said you made it with C, H, and N. Is that correct? So we know it has 3 elements in it. And we know that when you made this compound, the whole thing had a mass of this. This is the whole sample, the whole enchilada, okay? Enchilada. Now, then they did something weird. They reacted this compound with oxygen. What? What are you doing? What are you doing to my compound? I'm trying to figure out what the compound is. Well, then how is this supposed to help you? Well, here's what's going to happen. If you react with oxygen, oxygen can easily form a compound with carbon. And it did, carbon dioxide. And it said, this is how much it made. And then what else did it make? It made oxygen jumped onto hydrogen and made that. Now, for whatever reason, maybe it was the temperature that was at, whoops, I just made a mistake. I put the wrong number in the wrong place. Sorry. Oh, darn it. Okay, carbon dioxide is 1638. And the water was 1676. I'm sorry. Now, for whatever reason, they didn't get any nitrogen compounds. Okay, that's good. That's good. Even if they did, I could figure it out. So now what I want to know is, they want to know what the formula is, what the empirical formula is. All right, I'm looking at your faces now. Just be honest with me. Said, I have no idea how to approach this problem. I have less than a 50% idea how to do this. All right, I have less than 80% sure that I can do this problem. Wow, are you kidding me? How many of you are over 80% sure you can do this? Uh-oh. That's not 100% of the people, is it? Okay. So I'll tell you, the first time I saw this, I said, what in the world are they doing here? And so I had to take this apart. And I did not know Mr. Schilling was going to give that thing today, but what did he talk about? A problem that seemed complex. What did he say? Yeah, we can. And it might be able to make this thing seem simple. So what do we know is, out of this thing here, now this is the sample that contained all 3 of them, isn't that right? A certain amount of those grams are over here, aren't they? With oxygen. So how many grams of carbon are over here? So how in the heck am I supposed to know? Well, remember percent composition? Everybody got percent composition? All right, tell me right now. If you know percent composition, what percent of this right here of carbon dioxide, what percent of carbon dioxide is carbon? Can we do that? What's the percent? Total 44.
What's the
How much is it?
You're talking about carbon?
Yeah.
Is it 0.6?
I don't have that. I don't think. Wait.
The amount of the.
Oh, this one, 0.1638. Dang it. 0.1638.
Okay.
Sorry. And this is 0.1676. Sorry. All right, what's the percent composition in carbon dioxide? Isn't it 12 over 44? What's that give you? 0.27? Okay, we know that 0.273, is that right?
Yeah.
Now, real quickly, take your calculators and say, what's 0.273 times that? If it's 27% carbon, then how many grams is that? So 0.273. All right, how many?
0.0447.
All right, 0.0447. Good job. Okay, now, so guess what? I know how many grams of carbon are in there. You see that? Where did I get this carbon? From here. This carbon, when I combined with oxygen, made CO2. What percent of any amount of CO2 is carbon? It's 12 out of what?
44.
Out of 44? That's 27.3%. So, if 27.3% of carbon dioxide is carbon, then what's 27.3% of this carbon dioxide? It's this many grams. I'm already there. I'm almost there. I know how many grams of carbon there were. Now, These are grams of carbon, right? Let's go over here and do the same thing. I want to find out hydrogen. How many grams of hydrogen?
How many grams?
That's 0.1676. I apologize for that. All right, what's the percent composition of hydrogen in water? And when you do these faster like this is how you pick up speed. Kayla, you have this one in your head a bit?
11.1%.
You're right, because it was 2 out of 18. That was 0.111, wasn't it? 11.1%. So that's go up here and multiply. If 11% of water is hydrogen, then what's 11% of this water here? How much? 0.0186. That's what I got. Okay, good. Now, can you see where we're at?
We have the carbon and the hydrogen.
I need one more. Uh-oh. Christina's going to tell me. I never call on you. That's my fault. Christina, how can I find how many grams of nitrogen? You can do it. Yes.
Whatever is left.
Yes, that's exactly right. Now tell me what numbers.
We have 0.0447 plus 0.0186, and then you'll subtract that from 0.115.
You are exactly right. This sample contained only 3 elements, right? And you figured out how many grams of this was carbon, how many grams of hydrogen. Whatever's left has to be nitrogen, doesn't it? So it said this minus this minus this. And somebody get me a hit on that.
Do we,
Wait a minute. I need a hit on this one. 0.0523. That's what I got. Everybody get that? Now, when you first saw this problem, I think it was difficult. It was difficult. Tim.
Do we need to be careful to use, is it okay if we use less than the number of sig figs that we got?
I wouldn't go below 3.
Okay.
I honestly would not go below 3, okay? Now, let's do some shortcuts. Here's some grams. You're not going to get a formula out of grams, aren't you? Guy get in the mole world, what's your shortcut? What is it? By the molar mass. Molar mass. Okay, what's the molar mass of carbon? 12. What's the molar mass of hydrogen? 1. Molar mass of nitrogen? 14. Here we go. Give me some numbers here. Who can I call on? Jeb, you done with this yet? Carson, you have these numbers? Can you give me a hit on this, like 0.0447 divided by 12? Okay. All right, say it again. 2.5? Okay. And next one? I beat you. That's divided by 1. And then this is moles. Moles. And this one? What do you have for this one, Jim?
Or wait, should we do 14?
Is this 0.0033736? Something like that? Now, here we go. We've been here before. I'm in the mole world. But I have some ugly looking numbers looking at me. How are we going to tame those numbers? Divide by the smallest. Yes, everybody okay on that?
Sorry, are we dividing n by 14 because...
Okay, the shortcut from the gram world, what's the shortcut from grams down to the mole world?
Divide by the molar mass.
Okay, so the molar mass of nitrogen is
Well,
4.
that's nitrogen too, right? Are we doing...
Wait now, this is nitrogen, the element that happens to be in a compound. It's not just nitrogen. What now?
Isn't our compound CHN?
Yeah, but all they said is a compound made of 3 elements. This is not the empirical formula. They just said they made a compound with carbon, hydrogen, and nitrogen. That's all they said.
So because in the environment we never run into n by itself, we just go...
Okay, I'm gonna make sure that's clear. The only time nitrogen is diatomic if it's by itself as nitrogen gas. You get that? I can have as many N's as I want in a compound. I could have 27 N's in a compound, right?
Sorry,
No, that's a good question.
I got the molar mass and the.
Right, okay, now, the smallest number here is 0.003725. I'll bet that's gonna come out to be 1.003725. I'll bet that's gonna be really close to 1, isn't that right? Now I need this one. What's this one? 0.003725. What do you get here? Do you have this one?
Yeah.
What do you got?
It's 5 in the middle.
And let's see. That's what I got. Very good. So now I'm ready to declare that the empirical formula is what? For every 1 carbon, there should be 5 hydrogens and 1 nitrogen. Now I'll make up a number for you, okay? That means the real compound could be, what's the mass of this guy here? 12 plus 5, 17 plus 14, 31. Okay, so this empirical formula has a mass of 31. What if I do another experiment and I find out the mass is 31? Ding, ding, ding. Then that's him. What if I find out that the molar mass, what if the molar mass is 62? Well, then you can't be the real compound, can you? You can't be the real, because the real one has a mass of 62 and you're 31. So what am I going to do here? 31 goes into that how many times? Twice? Well, let's double it. Then the answer is C2, H10, N2. This should be the easy part. If you have the empirical and they give you the molar mass, you should practice that all day. They give me a whole page of those. I'm going to get those right. What do you think? All right. Now, in the time remaining, I'd like you to, before we come back, I'd like you to be able to do this on page 110. On page 110, I'll tell you what. Let's do a 111. If you go to a we can do a 110. We go 10. Here's what I'd like to do. On page 110, they have a problem. And I know it's the last period of the day. Some of you are pretty tired looking, is that right? Okay, thank you for staying with me this long. You did a good job. Let's go to page 110 at the bottom. And here's our problem. These are great problems. If you have time to sit with your book and say, I could do this for half an hour. I could maybe do it for, Look on 110. Nitrogen gas can be prepared by passing gaseous ammonia over solid copper 2 oxide. So here we go. It says nitrogen gas can be prepared. So that means it's going to be a product, isn't it? By passing ammonia. What's ammonia? NH3, okay, over copper 2 oxide. +2, -2. And it says here the other products of the reactant are solid copper and water vapor. You know what? Is this one of those that I had on my handout sheet?
I think so.
Is this the same one we did in the handout
Yeah.
sheet? Okay. Oh, well. Anyway, let's go ahead and balance it then. Read. How fast can you balance it? Oh, what do you think? There's an odd even right there. Is that odd even? I'm going to try a 2 here. I'll try a 3 here. Let's see if that fixes it. 6, 6, 2, 2. 3 oxygens. 3 oxygens. 3 coppers. Does that do it? Okay, so don't do stoichiometry unless you have a balanced equation. All right, let's do shortcuts. First of all, it says here, a sample containing 18.1 grams of that reacts with 90.4 grams. Now, ding, 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 ding. Little bell better be going off in your head right now. Limiting reactant. If I give you the grams of each, or the moles of each reactant, well, you ready to do the 2 rows of boxes? Remember that? Now, when you go to college and you see people not doing that, you'll say, what are you doing? And they could have been taught another way. I'm fine with that. I'm fine. If you learn another way, I'm fine. But here's what I do. I put an asterisk here, an asterisk here. Then I put a star here and a star here. All right, let's do some molar masses. Molar mass of ammonia. How fast can you do that? How about molar mass of this is what? 14 plus 3? 17. What about copper oxide, copper 2 oxide? And 63.5 plus what? Everybody should know oxygen, right? How much is it? 63.5 plus 16? Everybody got that? And then they're going to say, they want to know how many grams of N2. So if I had this on a multiple choice test, okay, and it's all set up there, and let's say I balance it, they really only want to know this. That's all they want to know. I don't even have to do this. You get that down there? So let's see how fast we can do it. You ready? You want to see how fast we can do it? Everybody clear your calculators? And what I'm going to do is, tell me how many moles that is. 18.1 divided by 17. What you got? At least 3 sig figs, right? That's good. Now, let's go down here. How about this? 90.4 divided by this. 90.4 divided by 39.5. Again,
1.13.
as soon as I fill in that box there, I will declare who the limiting reactant is. Now, here's how we do it. Ready? I'm going sideways, aren't I? 2, 3. 2, gotta get bigger. What are you going to multiply? Going sideways, I use the coefficients, don't I? You're going to multiply by what? Is 3 halves going to make it bigger or 2/3? So multiply by 3 halves. What do you got here?
1.605.
Okay, I'm all right with that. I'm ready to declare the limiting reactant. Here we go. I have this much peanut butter. If you brought this much bread, you'll use up all my peanut butter. Did you bring this much bread? Then you are going to limit how many sandwiches get made. So the limiting reactant is copper 2 oxide. And whatever row of boxes are in that, that's what's going to happen. This is what's going to happen, not this. So now we go around and have some fun. 3, 3, matchy matchy. We'll do that. There's another 3, matchy matchy. Okay, and then here's 2, and how about this one? 3, 1, 3. Gotta get smaller. Gotta get smaller. What is this divided by 3?
0.377.
Man, you're fast. Okay. All right, we're almost ready. Let's do one more. Ready? Gotta get smaller. Gotta get smaller. I'm going this way. Multiply by 2/3. What's this one? One more. We can do it. Point what? 0.75 even? Even? Okay. Okay, now, ready? Now, what do you want to know? Well, how many grams of N2 are going to be made? Whoop, whoop. When you want to pump out of the mole world, you multiply. What are you going to multiply by? Oh, by the way, N2 is 28. So take this times 28. How many grams?
10.56.
One more time.
10.56.
6 point.
10.56.
All right. We look in the book, and it says on page 111, it says 10.6. That's how the author uses sig fig rules all the time. What do you think? All right, one more question before you leave. How many grams of the excess reactant are just sitting there and they never did react? How many grams? Who's the excess reactant, first of all? This guy? I brought this much peanut butter. Well, I didn't use it. I only used what? I only used this much. So now, that'll tell me how many moles. This will tell me how many moles were left over, and how you change moles to grams. Multiplied by the molar mass. Hey, I know we did a lot today, and what I would do is if you don't have time tonight, maybe tomorrow night you could do something like this.